Hi, this is the proof for the fundamental theorem of calculus part 1, and I'm just going to give you what the fundamental theorem of calculus part 1 is if you have a definite integral and it's within the interval a to b, and you're computing the area underneath the curve of f of x dx, you can compute that area by taking the antiderivative, which I'm going to call capital F, substitute b in, and subtract from it the antiderivative with a in it. This is the fundamental theorem of calculus, which I call FTC Part 1. And we're going to look at the proof for this. And it's going to look like this. First of all, I want to write down what the definition of an indefinite integral is. And so here's my definite integral. And the definition of this is that you're really adding up an infinite number of rectangles, and you're computing the area of those rectangles. And here you're going to be plugging in f of c times delta x. This is where delta x is equal to b minus a over n, and c sub I equals a plus b minus a, or delta, let me just back up here a little bit, I'll give myself a little delta x I. Alright, so that's our definition of a definite integral. And so what I'm going to do here is I'm going to draw a little picture. And right here I'm going to have A, and right here I'm going to have B, and I'm going to draw a function here, and this is f of x. And so I'm looking at the area underneath this curve. And inside here I can break it up or partition it up to a bunch of different little segments. And like this is x sub 1. This right here would be x sub 3. And so if I do that, A is going to be the beginning of that, what I'm going to call x sub 0. And B is going to be the last one of that, which I'm going to call x sub n. Alrighty. And if you take a look at this, if I'm looking at f of b minus f of a, f is a function. It just happens to be the antiderivative of lowercase f here. And so if I substitute b into that, I'm actually going to get a y value. And if I substitute a into that, I'm going to get a y value. So I can look at the y-axis. And somewhere here, I'm going to have an f of b. And somewhere here, I'm going to have an f of a. And f of b minus f of a could be viewed as the distance between these y values. Well, there are little tiny distances in between here. So there's a distance between these two, and there's a distance between these two, and there's a distance between these two. And this right here, since f of b equals f of x sub n, this distance right here could be viewed as f of x sub n minus 1. And down here, this little spot right here could be viewed, since this is the same as f of x sub 0, this could be viewed as f of, if I'm just one above it, of x sub 1. And so I can say that this distance from f of b to f of a is really a whole bunch of distances that are being added together. It's this distance, f of x sub n minus f of x sub n minus 1. That's a distance. So I'm going to put brackets around it. And I'm adding to it this distance, f of x sub n minus 1 to f of x sub n minus 2. Okay, so that would be this next distance, and I can keep adding all those distances. So I'm going to put 3 dots here, which means there's a whole bunch of stuff in here. And I get to this last one, which is f of x sub 1 minus f of x sub 0. So all I'm really doing is I'm simply saying this distance is a sum of an infinite number of distances. So then I can rewrite that. Since I use the word sum, I can write it in summation notation, and that this can be replaced as the sum as I goes from 1 to n of these distances, f of x sub I minus f of x sub I minus 1. So you can take a look. When I is 1, I'm going from x sub 1 to x sub 0. That's this one right here. And when I get up to n, I'll have f of x sub n minus f of x sub n minus 1. So I'm getting all the infinite distances there. All right, so I'm going to take, and that's my first part. I'm going to take a little break from that, and I'm going to talk about the mean value theorem. And the mean value theorem says this. The mean value theorem says that f of b minus f of a divided by b minus a has to equal to the derivative of f at some c that's between a and b. And this right here, if you recall, is the slope of a secant. And this is the slope of the tangent line. Okay, and we've talked about that before. Well, you know this, that f at some c sub I, the derivative of that, excuse me, can be written in this form, lowercase c sub I. And now what I mean by c sub I, it's simply a c within this interval between x sub n and x sub n minus 1, between x sub n minus 1 and x of n minus 2, somewhere in between those segments. And I'll use my semicolon here. Delta x sub I is the change or the difference between those consecutive x's. Okay, so just a little bit of notation there. So that means I can go from this to saying that I have f of x sub I, okay, that's my b, minus f of x sub I minus 1. And that is equal to the difference between those, x sub I minus x sub I minus 1. And that is equal to the derivative of c sub I. And that can be rewritten as f of x sub I. Now here I'm going to do some substitution. Down here I'm going to write delta x sub I. And right here I'm just going to use my lowercase f. Okay? So all I did was substitute these values right in here to here and this to there. Alright? So I'm going to need more room, so I'm going to get a new page. And if you recall, I left with this f of x sub I minus f of x sub I minus 1 over delta x sub I is equal to lowercase f c sub I. Alright, so I'm going to multiply both sides by delta x, and I have this. Is equal to this product, f of c sub I times delta x sub I. Alright. From the previous page, I stated that f of b minus f of A could be written as the summation of a whole bunch of areas. And that's what I'm going to rewrite right here. Okay, and that means I'm going to write that underneath here. Okay, so here's the heights, here's the widths of all those rectangles. But this is also defined as this. That's the definition of a definite integral. So that means I can substitute this right in for that. So this is the definition. Okay, this is the proof of taking the antiderivative of lowercase f and substituting b and then substituting a into those antiderivatives and subtracting give you the area under a curve.